something strange happens. It's as if it is deflected by an invisible shield, the Earth's magnetic field, the magnetosphere. The magnetic fields couple together and create a funnel for the gas streams down on the daylight side of the pole. This is the daytime aurora, which our eyes cannot see. The magnetic fields stretch further rearwards and couple together. The magnetic fields, stretched like a rubber band, break, and gas from the solar storm streams back along the magnetic lines towards the polar regions on the night side. This is nighttime aurora we can see. We can see.
This is Houston. Say again, please.
Houston, we have a problem.
And using parallax to find out how far something is nothing more than trigonometry.
So we're going to use trigonometry. I've got a formula set up for that right here. I'm just going to punch in the numbers and it's going to give us the information. So basically between 2 points and up to the moon, we're going to measure how far the moon is.
And finally, we now have everything we need for our equation to solve for x. So x will represent the distance from the moon to my location in Florida. So we simply plug in the values where they belong, crunch them out, and what do you fucking know? We found that the moon is 224,573.102 miles from my front door.
Okay, so it's 224,573 miles. Okay, so let's see what we get. Let's plug in 89.4 because we had to account for Earth's curvature, and forgot that there we go. So we have to account for Earth's curvature, which gives us a parallax of 0.6, which makes this 224,573.1. Is that right? 224,573? 224,573.1. Okay, so this formula works. But what if the Earth is flat and we put in 55.4 for this degree? We go back to her original degree that she had. Oh, wait a second. Now the moon is 3,409.143 miles away. So let me just ask you a question. Does the moon look like it is 3,409 miles away? Or do you think it looks like it's 224,500 miles away? Use your own observation. Let's see what the ending is here.
The conclusion is that your assertion that the moon is only 3,000 miles away is horseshit. So, Duranus.
So, I've got to ask you, based on the formula, is it 3,000 miles away? Or is it 220 whatever thousand miles away? Because he seems to think that he's absolutely correct, but I've just proven that, well, if the Earth is flat, it says that it is 3,000 miles away, and he's wrong. So you just got to make the decision. Formulas will tell a different story depending on what the reality is. Depending on what the reality is. Depending on what the reality is.
And as I love to point out and have pointed out many times, I will never get over the idea that the coincidence of the fact that if you look at the moon, and when TJ did his triangulation, he came out, he and Red, right, came out with a distance to the moon of 3,409 miles, which is really close to my 3,415.9 miles. But here's the cool thing about the numbers in this, and I had to bring this up because I just think it's so amazing. But 3415.9, okay, I don't need to tell you how close that is to pi, just as far as the numbers go. Pi being 3314159. Get rid of the 1, you've got 3415.9. That 3415.9 miles up translates to precisely 180,360,00 feet. If that is just too bizarre, and if that isn't bizarre enough, when you plug in that 180,360,00 feet to a distance to the horizon calculator, you get a distance to the horizon of 6225.0 miles, which is precisely 1/4 the circumference of the Earth. And if you were to project a light up that high in two directions, you would have a light that covers precisely half the circumference of the Earth. Now, that is just too weird, people. And this whole mathematical construct works out in really weird ways. And if you think that isn't weird enough, you would go ahead and start plotting out the orbits of the planets around the sun or the Earth, even in the heliocentric model. And what you come up with is an absolutely mathematically perfect, beautiful spirograph design, right? What is up with that in a Big Bang universe where it's all chaos? Where is this symmetry coming from? Well, it's coming from the math, and it's also coming from the fact that this is a created construct, guys. Of course there is logic and reason and divine numbers involved, because it is not a cosmic accident. There is order to this chaos. And whether you want to admit that or not, it's the way it is. So what I want to do then is let's just take this a step further, and let's keep it in the realm of observation. All right, and let's just say Red's rhetoric was right, okay, and there is this 0.6 degree of parallax on the Earth. And let's take, and since we have the sun and the moon in the sky, and they are both, of course, the same apparent size, we can do that very, very same trigonometry on the sun. Absolutely we can. And if we were to do that, what do you suppose is going to happen if we did that trigonometry on the sun between California and Florida? Well, I can tell you what it's going to come out to be. It's going to come out using Red's own formula and observation, measuring angles to the sun. It's going to come back showing that the sun is also 224,000 miles up. Whoops.
Yes.
That's a problem.
Yes.
Houston, we have a problem.
The Aurora Borealis, perhaps the most amazing phenomena on Earth. It's been seen from Earth's surface and even from space. We can see the aurora when charged particles from the sun collide with the edge of Earth's atmosphere. For the first time ever, we used a high-altitude balloon to fly to the stratosphere and film the aurora from the edge of space. We flew a state-of-the-art camera and electronics to video record the entire flight, and a Geiger counter to measure radiation levels as it approached the aurora.
5, 4,
this is what we found.
2, 1.
Those charged particles, again, moving through a magnetic field, they also create a natural radio signal. So when you see aurora, again, very low frequency receivers can turn the sound, turn those signals to sound. So this is the sound of aurorae here on Earth. And there are all kinds of other signals. There's one called the dawn chorus, which sounds like little birds. Instead of that sort of noisy chatter, it's little birds tweeting. You get all these kind of radio signals for the interaction from the solar wind and our magnetic field.
When nature really puts on a show, it also gives itself a much-deserved hand. For years, folktales and first-person accounts from the Aurora Borealis have claimed the dazzling northern lights also produce strange noises. And now scientists have found those noises, which are apparently similar to the sound of clapping hands, 230 feet above the ground. Researchers from Finland confirmed that, quote, the source of the sounds that are associated with the Aurora Borealis is likely caused by the same energetic particles from the sun that create the northern lights. They don't occur during every appearance and they're usually brief and faint, but can vary from claps and crackles to muffled bangs and sputtering sounds. Because the noises are so diverse, scientists don't yet know for sure what's creating them. But they are definitely there in the atmosphere. Mother Nature, bringing you the soothing sounds of Rice Krispies and Pop Rocks from space.
This is Houston. Say again, please.
Because the noises are so diverse, scientists don't yet know for sure what's creating them. But they are definitely there in the atmosphere. Mother Nature, bringing you the soothing sounds of Rice Krispies and Pop Rocks from space.
have a problem.
From space.
All right, so we have here Time Storm Films. So the question is this for real? Because I find that the North Pole and the South Pole are oftentimes different in like every way, because the southern latitudes are just not what we're told that they are. It's something different. It's something completely different. So, so the question is, how is an Aurora Borealis different from an Aurora Australis? And my hypothesis is because one is like real, the north one is very strong, and then the southern one, though I contend may exist, it certainly is not the same in its appearance, its strength, etc., because instead of converging on a single point, I think it diverges out to a large ring. So that is one reason. The other reason is it seems that we can't get any really good verifiable information from anybody, including images or video, south of 60 or 70 degrees latitude. So the Aurora Borealis and the Aurora Australis are lights of the northern and southern hemispheres, respectively. Well, yes, I know what they mean, respectively, but nothing is respective in the south versus the north, it seems. Not population, not fauna, flora, all that stuff is completely different, along with temperatures and everything. So there's a reason we call them the northern lights. You know, it's that's where you see them. And again, the problem, the southern lights would be seen in the high latitude region of the southern hemisphere, but nobody's there ever, it seems, like hardly ever. While the northern lights are observed best around dawn, it's around dusk that one gets the best views of the southern lights. Why would that be? Why? Why would that be different? Now, the northern lights can be seen a couple hours before dawn and right after dusk. And then they say further research contends that the same is true for the southern lights, but it's probably actually not. Otherwise, why would it be a thing that you don't see the southern lights around dawn? And what would be the reasoning for that? I find it curious. The ideal months for viewing the two differ, but that's obvious. I mean, come on. I mean, that would make sense on a globe or anything stupid like that. Well, a globe the size they say it is. Well, the northern lights, let's see. Ding, ding. Skip down. It's easier to spot the Aurora Borealis. Well, yeah, that's my hypothesis. Right there, they say it. The reasoning behind it is the entire geography, shape, geographical form of the Earth is completely different from what they say. That's my answer. But they just guess about other... They make less educated guesses. It's much easier to spot the northern lights vis-a-vis... What? Perhaps the most obvious reason for the difference in popularity levels of the two auroras is that it is much easier to spot the northern lights vis-a-vis the southern lights. No, not vis-a-vis. Versus. But why? Okay, let's see what they say. I want to know why is it difficult to see the southern lights? Chaw. That looks like CGI. Fake. There. Image source, whatever. As they say, it's all about the land. Lex Luthor. Mr. Luthor. Land. Much of the area under the belt of the Aurora Australis is in Antarctica, which is a huge chunk of ice. No, it's supposed to be a continent of land, a huge chunk of ice surrounded by waters and icebergs. It's hard to reach there, only because they make it. And even harder in extreme winters. In other regions, the topography doesn't always assist the viewing experience. Well, isn't that convenient? Maybe we're on to something here, as per usual. You're at the UAP channel, by the way, but you already knew that because of what's happening. Yeah, this is happening. Yes. Canada, Alaska, Greenland, Iceland, Norway, northern Russia, northern Scandinavia, on the other hand, provide enough land with good topography for amazing views of the northern lights. Okay. So you can't get on a boat and go see it? Much of the area under the belt of the Aurora Australis is in Antarctica, which is a huge, did I already read that? I gotta get better at this. I guess that's it. They don't extrapolate any logic or hypothesize any kind of educated guesses based on the vast amounts of data and knowledge that we have from all that scientific research being done down there. Oh my gosh, just tons of it. How much money has been spent on that? It's incredible. It's a whole continent of scientists working day and night to figure out these types of questions. All right. 0 comments. Well, let's continue then. Southern Lights. Have you heard of the Aurora Australis? Probably not. No. Or move over, Northern Lights. Ugh. The new kid on the block. New? Shouldn't it have always been? Shouldn't we read about it in the ship's logs of sailors who cut through the high latitudes of the southern hemisphere to shorten their trips between the southern continents? It's the new kid on the block, though. Aurora Australis is just the kind of beauty you would want to have on your travel bucket list. But I put it in there because that's what that big space is for. While the northern lights are on the bucket list, and rightly so, a lot of travelers, they are not only the beautiful light phenomenon on the planet Aurora Australis, the lesser-known sibling of the Aurora Borealis, the red-headed stepchild as far as auroras go. The northern lights is just as beautiful. Really? Can you say that with confidence scientifically? But, there is a but. There is a but. It's all about the butts. About the butts. Before you put that butt on your travel bucket list for the year, read on to know more about the phenomenon and the best places to see the Aurora Australis. There will be music playing that is similar to a planetarium, because I'm already going to do that, but I have something else planned. Anyway, I'm giving you a taste of it right now. What are the southern lights and the northern lights? Well, we know what the northern lights are. Well, what they say they are. I'm not going to go so far as to say that. Oh, look at that. Is that the Tower of the North? What is that? The literal North Pole? No. But it does look like something that makes me say, which it does, it makes me say, curious. Very curious. All right, so I'm going to skip all the stuff that scientists like to think that we don't know. Magnetic field and particles and all that crap. And the colors. Okay. From where? This is what I want to get to. From where can you see the southern lights? Well, there they are, pictured in all kinds of artistic glory. Almost too much to be believable. Looks like Photoshop to me. Number 1, Antarctica. Yep. Yeah, clap your hands, everybody. We're going to Antarctica. Yeah, it's so easy to go. Pack your bags. We're going to see the Aurora Australis from the South Pole, because people go there all the time. Yeah, their flights. Yeah. Oh, wait. Maybe it's more like Truman trying to leave his little dome in Hollywood. Oh, they got pictures. The best place to see the southern lights, is the continent of Antarctica itself. The southern lights are most impressive, most active, and most visible here, especially during the months of March to September. Okay. Do we have to take your word for it, or can we go see it on our own? Well, let's see. But with the best views, comes certain difficulties. Oh, I'm sure. The ways to get into the continent during winters are filthy expensive. Filthy expensive and dangerous. I bet they are. The temperatures are as low as negative 50 degrees C. Howling gales and dangerous ice packs are what define the winter topography of the area in winters. But those who can musher, or muster, but we'll mush the dogs. You can't bring dogs, though. The strength and the money to be here in winters are sure to witness an amazing light show in the best place to see the Aurora Australis. Oh, yeah. Yeah. It's like a car salesman saying, buying this car is just the best decision of your life. Just wait until people see you. It's worth it every bit, and it's more important than money. It's more important than anything that you buy this used car from me right now. Except he's actually selling it, whereas here they're just selling the idea of it, but then they say, you can't. It's too dangerous, too much money, too many things to make it impossible. But trust me, it's the best thing ever. Okay, let's move along. Number 2, South Georgia Island. Well, okay. Yeah, penguins, schmenguins. Penguins. One of the southernmost islands of the world, South Georgia, finds itself encased by ice. Blah, blah, blah. Yeah, cool. But the island, located in the southeast of Argentina, can be easily reached during the months of March to September. Okay. Polar cruises are the most popular ways to get to the island. All right. So, okay. So let's see. The Antarctic winter, beginning in the month of March, offers dark skies that are perfect for viewing the southern lights. But to leave any time after March for this island with no permanent residence is just too dangerous. Now, let me analyze this a little bit, because if we go back and we see South Georgia is encased by ice. Okay. When would it be encased by ice? During the winter. When would the winter be? From March to September. Okay. So when they say that the island can be easily reached during the months of March to September, and polar cruises are the most popular way to do so, they're saying that I think that actually that you would be reaching the island between September to March in those months. What would be the winter in the north, be the summer in the south, and that's when it would logically be easier to reach. So they said it wrong. Now, is it a mistake or is it on purpose to confuse things? I believe it's probably a mistake. But certainly things are confusing when it's another place. It's a place you can actually go to, okay? But you just can't go there when the aurora would be visible. It's just too dangerous. I guess you could go there and stay through the winter, but I wonder, does anybody do that? Do very many people do that? And do they see the aurora as reported? It's a question. I don't know. I think it's dubious. One of the southernmost islands in the world, South Georgia finds. So, okay, I read that. So forget that one. So 1 and 2 are out completely. Pretty much. Number 2 is still a little bit of a question mark. I'd say out. Number 3, Ushuaia. I don't know if that's the right way to say it. I'm just hooked on phonics there, trying to do my best. What the heck is that? Okay, whatever. Located in the far south of Argentina, Ushuaia is perfect for viewing the Aurora Australis, or the Southern Lights. Despite its location down south, it takes a considerable amount of luck to merely spot the Southern Lights from Ushuaia, and you have the poor weather of the city to blame. You poor weather. I just can't stand it. Like that? Okay. I'm already practicing for my failure in going there, and failure to see the Aurora Australis. The persistent cloud cover makes it impossible to see the aurora, even if the sky lights up. Yeah. The city has its own airport. Oh, we can go. Hey, we can use that airport to go not see the lights. Thanks for the sales job. So getting to Ushuaia should not be a problem. To not see the lights? We can get there, no problem, to fail, to not see the lights. And to increase the probability of spotting the aurora, which the aforementioned statement says is impossible to see, try heading to a more remote place close by to avoid any light pollution. Good luck with that. That's when they lean back and they relight their cigars that burnt out, and they kind of chew on them and curl their lips around their teeth, and they make that kind of special sound that they do. As the chairs squeak as they lean back and forth, yucking it up, shoulders bouncing. All right, I'd say that one's out. What do we got? Out of 5, I think? I don't know. We're up to number 4. Those Falkland Islands. All right, the Falkland Islands. Are you out of your Falkland mind? The lesser-known Falkland Islands are home to about 2,500 people and boast an outstanding beauty and wide variety of wildlife, penguins, seals, and much more. Like different kinds of penguins, and emperor penguins, and various varieties of seals. You have your whiskered seals, and you have your baby seals, and all kinds of different seals. The island's importance for the Aurorae is evident from the fact that a monitoring system has been closely recording the activity of the Southern Lights since 2010. Is that about when they were discovered, invented? Like what? With myriad stay options and air and sea connectivity, the islands of Falklands make a great vacation spot. I bet they do. And the darkest months of April to August increase the chances. Oh, it's not a given, it's just a chance. This is the first somewhat realistic of the top places to see it, and it's just a chance of spotting the lights in the sky. Best time to visit the darkest months. So they kind of intimate that it's possible to see the lights there, but definitely not a guarantee at all. Chances. That's what chances means. So, okay. Help us, Stewart Island. You're our only hope. That's my Princess Leia impression. I never thought I'd do a Princess Leia impression. I'm going to try it again. Help me, Stewart Island. You're our only hope. All right. You notice when, in that scene, and she's like the 3D hologram, and it's kind of this bluish light, kind of translucent. And then that's kind of turning out how those things will be like when they actually happen sometime. Isn't it kind of weird? How would they have known that if it turns out to be that way? I find it curious. Anyway, it's neither here nor there. Stuart, it makes me think of Stuart Smalley. I'm good enough. I'm smart enough. And doggone it, people like me. And at Stewart Island, you can see the Aurora Australis. It's the closest you can get to the South Pole besides Antarctica. It's Rakiura National Park literally means the land of the glowing skies. So that sounds promising. It's just a name. Can you actually see it? The long hours of darkness in winters coupled with the sparse population and the low levels of light pollution enhance the view of Aurora Australis. Location, southern tip of New Zealand. Best time to visit, Antarctic winter between March and September. Okay. So that does sound promising. Okay. Maybe it's possible then. So I would like to know, can it be independently verified? Because I can't do that. So now we have Hobart. That looks like a real picture almost. Yeah, that's promising. Okay, we're getting somewhere now. The capital and most populous city in the Australian island of Tasmania is a popular place to see the Southern Lights. But large mountains, trees, and light pollution city are often obstructions to the beautiful Aurorae. Therefore, nearby locations like the South Arm Peninsula, Dodges Ferry, and Cockle Creek are often preferred for viewing the Southern Lights in Australia. Okay, so that sounds very promising. Maybe we're getting somewhere here. All right, good. I find it fascinating. Okay, so how is it different? Well, see, that's what I would like to know. So since I haven't seen it myself, I can't really see it I know Flat Earth Brothers are going down to Australia. I know a lot of you are Australian. Let's say it way. You do. And I have many New Zealander fans. You know, down under folks. So I just wonder, have you guys seen it? And, you know, so in the comments, please.
But what exactly causes these mysterious light shows? Let's find out. Some Inuits believe that the spirits of their ancestors can be seen dancing within the lights of the Aurora. The Vikings believed that the Aurora was a bridge of fire to the sky forged by the gods. Well, spoiler alert, according to modern science, the northern and southern lights are not dancing spirits or a bridge of fire. They are actually caused by something much more tangible: the sun. Our sun is a 4.57 billion year old ball of hydrogen and other gases fusing away in space, 150 million kilometers away from planet Earth. And every once in a while, it kicks up a bit of a storm, a solar storm to be precise. The sun produces energy by smashing hydrogen atoms together in its core under such immense temperatures and pressures to cause the hydrogen atoms to fuse, to form helium atoms. This process is known as nuclear fusion. When atoms are under these kinds of pressures, they turn into a mushy soup of freely moving particles, which is a fourth state of matter known as plasma. The sun is essentially a gigantic ball of swirling plasma. Using the process of nuclear fusion, the sun is able to turn small amounts of matter into enormous quantities of energy. It's how the sun has managed to keep producing energy for billions of years without running out of fuel. If humankind were able to consistently replicate nuclear fusion here on Earth, we would be able to make almost infinite amounts of energy using relatively little resources. In fact, if you could convert the mass of one bag of sugar into energy, it would be enough to drive a car non-stop for 100,000 years. All this plasma swirling around within the sun generates huge magnetic fields. These magnetic fields are under such immense pressures within the sun that sometimes the lines of force of these magnetic fields meet. When this happens, the magnetic field is forced outwards towards the surface of the sun. Once it reaches the sun's surface, it ejects outwards into space at great speeds, taking extremely hot gases and charged particles, also known as plasma, with it. This is known as a solar flare. And they can be witnessed on the sun's surface as a very bright spot followed by a cloud of gas. When a very large solar flare occurs, containing a significantly huge amount of energy, it is referred to as a coronal mass ejection. Or CME for short. The gas clouds produced by a CME can sometimes be larger than the sun itself. CMEs and solar flares don't stop just outside the sun's surface. Charged particles ejected from the sun continue to travel outwards through space over enormous distances. After travelling through space for around 2 days, they will reach planet Earth. This is known as the solar wind. It's a constant threat on planet Earth, and it can be extremely dangerous. If the magnetic field released from a solar flare or CME were to hit planet Earth, it could cause the extinction of the human race. So, why hasn't it? After all, solar flares are taking place regularly on the sun's surface. Well, the solar wind does actually hit Earth. Often. But our trusty planet is well prepared. We have a defense system to protect us from the huge amounts of energy that the sun bombards us with on a daily basis. Just like the Sun, the Earth produces its own magnetic field. At the Earth's core is a ball of solid iron. The heat of this iron and the pressure of the surrounding Earth turns the surrounding outer core into flowing liquid iron. The movement of this outer liquid core produces a magnetic field that, luckily for us, encompasses the Earth. The Earth's magnetic field protects us from all sorts of harsh destructive forces that come from far away in space, including solar flares. This protective barrier is called the Earth's magnetosphere, and it extends thousands of kilometers into space. That sounds really large, but it's actually rather modest. Jupiter's magnetosphere extends over 7 million kilometers into space on each side of the planet. In fact, on Jupiter's night side, the side facing away from the Sun, the magnetic field which is emitted is so large that it reaches Saturn.
For some Colorado scientists, this day has been nearly 10 years in the making. A spacecraft built in Colorado just sent these pictures of Jupiter's Great Red Spot back to Earth. Just incredible. Now, we were there at Lockheed Martin 7 years ago when scientists tracked the launch, and they've been focused on this mission ever since. Melissa Garcia, outside Lockheed Martin Forest Night. And Melissa, they have reason to celebrate tonight for sure.
They certainly do, and they actually just finished their 7th pass around Jupiter. The incredibly detailed images that they have been taking for the past 53 days are still coming in to the company's control center here, and what they show is essentially rewriting the textbooks. Juno is the first solar-powered spacecraft to fly to the outer planets, and it's capturing images of Jupiter that are clearer and closer than ever before.
It was the first opportunity we've had to fly over Jupiter's Great Red Spot.
And liftoff of the Atlas V with Juno on a trek to Jupiter.
And launched in 2011, it took Juno 5 years to reach Jupiter's orbit. Now, a year later, it's taking eye-opening photos of the planet's Great Red Spot.
Looks like maybe five or six.
And it turns out what scientists once thought was a single storm is really made up of many.
We see that actually it's made up of a whole bunch of storms. It's almost like a storm of storms.
On July 10th, our Juno spacecraft completed its 7th perijove, or close flyby of Jupiter. It flew directly over the planet's iconic Great Red Spot, about 5,600 miles above it. All of the spacecraft's science instruments and its JunoCam imager were active, providing the first up-close look at the 10,000-mile-wide storm that has intrigued humans for hundreds of years. Juno's next close flyby of Jupiter will occur on September 1st.
The new pictures are giving us an amazing view of the 10,000-mile-wide storm, which is big enough to swallow the Earth. But the storm is changing.
It is shrinking in size. It's becoming more rounded and less oval in shape, changes in color. So this hurricane is changing, perhaps decreasing in some ways, and other little hurricanes are cropping up.
Astronomers believe that Jupiter may have been the first planet to form in our solar system. By learning more about Jupiter, we can learn more about the origins of our solar system and how life begins.
Anyway, back to Earth. Most of the sun's solar winds simply bounce off the Earth's magnetosphere when it reaches us. However, the magnetosphere has two weak spots at the north and south poles. At these two locations, the magnetic fields which protect planet Earth are much less prevalent than they are nearer the equator. This means that a very small percentage of the charged particles that come from the sun do make their way into the Earth's atmosphere via the two weak spots at the poles. When this happens, the electrons in the solar wind collide with oxygen and nitrogen atoms in the Earth's atmosphere. During this interaction, energy is transferred from the atoms in the solar wind to the Earth's oxygen and nitrogen atoms, raising these atoms' energy state and exciting them.
It's that there are like Lego bricks from which everything in the world is constructed. These Lego bricks are particles, and the particles are the electron and two quarks. It's a very nice picture. It's a very comforting picture. It's the picture we teach kids at school. It's the picture we even teach our students in undergraduate university. And there's a problem with it. The problem is, it's a lie. It's a lie.
This is Houston. Say again, please.
The problem is, it's a lie. It's a lie. It's a white lie. It's a white lie that we tell our children because, we don't want to expose them to the difficult and horrible truth too early on. It makes it easier to learn if you believe that these particles are the fundamental building blocks of the universe. But it's simply not true.
It's simply not true. Now, he's got to tell you here that we again, he said it's a lie, it's a white lie. Why they describe these as particles. Now, this chap is telling us that in amongst everyone else that are talking about these protons and neutrons and what have you, that we can construe, quite rightly, that they're particles. And he's saying they're actually not. But we tell you that so you can grasp the fact that there's something there. He's going to explain now exactly what it is.
The best theories that we have of physics
Theories
do not have underlying them the quark particle and the two quark particle. And the electron particle and the two quark particles.
They don't.
In fact, the very best theories we have of physics don't rely on particles at all. The best theories we have tell us that the fundamental building blocks of nature are not particles, but something much more nebulous and abstract. The fundamental building blocks of nature are fluid-like substances which are spread throughout the entire universe and ripple in strange and interesting ways. Okay? That's the fundamental reality in which we live. These fluid-like substances we have a name for. We call them fields.
And there you go. He's going to show a picture of a field there now, people. So there you have it. So he said they're very nebulous and they're abstract, or fluid-like. In a state of change or continual change, at an atomic level. So they're energy substances that are, these waves and fields, and that's what we're all made up of, not discrete particles as such. So I had to take my hat off to you, David, and say thank you very much for being open and honest. And I won't play on anymore. I just wanted to get this out there.
It's a lie. It's a lie.
When an atom gets excited, its electrons move into an orbit further away from its nucleus. These newly excited atoms need to release this newfound energy to calm themselves down and return to their baseline energy state. The oxygen and nitrogen atoms release this energy in the form of particles of light, or photons. The light they give out is what we call the aurora. This process of exciting atoms to cause them to release energy in the form of light is the exact same way that neon lights work. The aurora are simply Mother Nature's neon lights, executed on a far grander scale. The only difference is that nature uses this phenomenon in a far subtler way than to advertise strip bars. The aurora typically appears in vast curtains or waves of light, following a distinct line across the sky. They appear this way because they are following lines of force in the Earth's magnetic field. Yep, that's right, the aurora uses the force. The different colours of the aurora are caused by different gases in the atmosphere. Each gas emits a unique colour when it's excited. For example, oxygen gives off a green light when it's excited, which is the most common colour seen within the aurora. Nitrogen, on the other hand, gives off blue and red colours when excited. So, to summarise, when charged particles released from the solar flares on the sun's surface hit our planet at either the north or south pole, they interact with atoms in the Earth's atmosphere. Causing their electrons to move to a higher energy state. When the electrons drop back down to a lower energy state, they release photons, tiny little particles of light.
The problem is, it's a lie.
Which light up the night sky in a spectacular display of painted waves, following the natural magnetic field lines of planet Earth. Knowing how the aurora are formed may spoil the beauty for you. But I believe there's an even greater beauty in understanding the science behind one of nature's most breathtaking performances. So, if you're ever lucky enough to experience the aurora for yourself, just take a moment to contemplate on how truly marvellous and magnificent the universe really is.
The problem is, it's a lie. It's a lie.
Is named in reference to its chemical inactivity. The chemical property of this first noble gas to be discovered impressed the namers. An unreactive gas was suspected to be a component of air by Henry Cavendish in 1785.
We've all heard of him before.
Argon was first isolated from air in 1894 by Lord Rayleigh and Sir William Ramsay. Weren't they the people that fudged the constituents of air?
Oh, in that document. Oh,
in that document.
Yeah, that's right. Yeah,
they were, weren't they?
They were, yeah.
Or somebody fudged their book, didn't
Absolutely,
they?
yeah, because they just put in these figures. And it
Absolutely, of course.
Didn't tie in with any other bits.
Absolutely. University College London, by removing oxygen, carbon dioxide, water and nitrogen from a sample of clean air. They had determined that nitrogen produced from the chemical compounds was 0.5% lighter than nitrogen from the atmosphere. The difference was slight, but it was important enough to attract their attention for many months. They concluded that there was another gas in the air mixed in with the nitrogen. Argon was also encountered in 1882 through independent research of H.F. Newell and W.N. Hartley. And that's not J.R.R. Hartley.
From the Yellow Pages.
Absolutely. Each observed new lines in the emission spectrum of air that did not match known elements. Until 1957, the symbol for argon was A.
So they're looking.
Now it is AR.
Yeah, so they're looking for a particular colour in the emission spectrum.
In the emission spectrum.
And you could probably change that by processing whatever the air with it
processing the air in a different way to get a change in your spectrum colour. Absolutely, you can change certain physical properties about a certain gas in order to get a different. Anyway, even though it's the same gas as another gas that has a different colour flame. Anyway, this little apparatus on the left. There we go. Yeah, let's go on here. Here we go. Now, how do I get onto that? How can I click that off? I want to click that. Yeah, oh, there you go. Now, this is a device that Lord Rayleigh used to replicate Cavendish's experiment and isolate this gas. Absolutely, yeah. Now, all it is basically is you have a container, glass container, and you have two wires going into it, and they're covered in a glass sheath. Covered in a glass sheath, and as they go up, they run up inside an inverted test tube. And they're able to. There's a contact between the two wires, so they can spark. No, they're slightly apart. Slightly apart, sorry, so they can spark. There's a gap between the two. So a spark can be bridged, or a spark can bridge the gap, and obviously the spark will obviously affect the air that's above the liquid, the solution in that test tube. Yeah. One thing they do is that they send a very high voltage through those wires. Do they? Oh, I don't know. Because they use a Rumkoff coil. A Rumkoff coil of medium size. And I, just from the top of my head, after looking at Rumkoff coils, I'm sure that takes up to about 20,000 volts. 20,000 volts? So you're talking very high voltage. Well, not bad, especially in 1890. Well, especially from a Grove cell that only powers a very small voltage. Oh, right, yeah, because they use Grove cells, and Grove cells, as we are already aware, are just batteries made up of sulfuric acid with anode and cathode in. Yeah, basically. Yeah. You know, and the anode's connected to the cathode in another cell in a series. You know, amazing how they got all this stuff. You know, but what's important with this is that in the container, they use, in their words, if you get the text up, they had to use a specific substance. There we go. No, not this one. Not this one. The text that was on under the. Oh, that one. Yeah. Oh, that one there. Yeah. They used a specific. Yeah. Here we go. The gases are contained in a test tube A, standing over a large quantity of weak alkali. Absolutely. Now alkali. Potassium. Now we are going on an assumption that the alkali used in the jar is potassium based. So it could be potassium hydroxide, or it could be potassium. Well, let's see whether Ramsay or Rayleigh actually identified gave away what alkali they used. How would we know that? Because it would be in that document. Is it in this one? It's in this document. Yeah, this document is separating on finding argon. Argon, yes. On discovery of argon. Yeah. So what page do we need to go up to? 272. 272. 272. 272. Here we go. Here's 272. 272. Blah, blah, blah. Yeah, early experiments on sparking nitrogen with oxygen in presence of alkali. There we go. So in our earliest attempts to isolate... Wait there, can I close this off, this pane? No, I can't. Yeah, let's just go. There. In our earliest attempts to isolate the suspected gas by the method of Cavendish, we used a Rumkoff coil of medium size actuated by a battery of 5 Grove cells. The gases were contained in a test tube standing over a large quantity of weak alkali, and the current was conveyed in wires insulated by U-shaped glass tubes passing through the liquid round the mouth of the test tube. With the given battery and coil, a somewhat short spark or arc of about 5 mm was found to be more favourable than a longer one. When the mixed gases were in the right proportion and the rate of absorption was about 30 cc's per hour, or 30 times as fast as Cavendish could work with the electrical machine of his day. To take an example, one experiment of this kind started with 50 cc's of air. To this, oxygen was gradually added until, oxygen being in excess, there was no perceptible contraction during an hour's sparking. The remaining gas was then transferred to the pneumatic trough to a small measuring vessel sealed by mercury, in which the volume was found to be 1 cc. On treatment with alkaline pyrogolate, the gas shrank to 0.32 cc's.
Alkaline pyrogolate.
Alkaline pyrogolate. So let's have a little look what alkaline pyrogolate is.
Wouldn't that be
this one here?
This one here.
Note on the use of alkaline pyrogolate solution in gas analysis. Absolutely, of course. Isn't this wonderful? Let's have. We're not going to read the whole book. We'll just have a little look at the abstract.
Note on the use of alkaline pyrogolate solution in gas analysis.
Where do we need to go?
Just make it bigger.
If I can.
All you need to look at is what type of alkali are they using. Although alkaline pyrogolate has
I can see it already.
Yeah, although alkaline pyrogolate has been for long in general use for absorbing oxygen in gas analysis, it has also been known for almost as long that a little carbon monoxide may sometimes be given off during the absorption, thus making the percentage of oxygen found somewhat too low.
It was definitely pointed out by one of us, however, that with a solution made by adding 10 grams of pyrogolic acid to 100 cc's of almost saturated caustic potash solution.
Isn't that potassium?
That's potassium based, isn't it? Potash. Absolutely. Blah, blah, about 1.5 and containing blah, blah, yeah, sp.gr. About 1.54 and containing about 80 grams of dry potassium hydroxide per 100 cc's of solution. The formation of carbon monoxide is entirely avoided, so that the resulting analysis may be taken as correct to the second decimal place. If the burette is corrected for errors in graduation, due care is taken. According to that information, they're telling us that they used potassium hydroxide.
And
or potassium hydroxide.
Oh, well, yeah, potassium hydroxide
as
caustic potash, yeah.
Caustic potash, which is their solution, which is found in their
experiment.
Where's their jar? Where's their jar? In this jar.
Yeah.
They're using potassium-based material. Now, the potassium-based material, as far as we're concerned, what's going to happen in the spark in the top of that test tube is that the spark is going to create an awful lot of heat.
Absolutely,
obviously.
yeah.
And obviously the water will want to evaporate, which will take along with it some of the potash, some of the potassium hydroxide. Now, the potassium hydroxide is simply going to stain the air that's within that top of that.
In the test tube A.
In test tube A. I don't know if people can actually see that. There we go. That's better. Yeah. So in the space there, space A at the bottom of the test tube, bottom of the inverted test tube. That's where the spark's going to take place. You're going to get a lot of heat. The heat's going to evaporate the water that is close by, which has potassium dissolved in it. The potassium's obviously going to stain the air.
It's our understanding that this is where argon gets its colour from.
So the whole point of this video is to really make people realise that, like we've said many times before in many videos, and that is man manufactures, produces his products.
Absolutely.
Because we don't think there's argon in the air at all.
No.
We think that's just a load of rubbish.
Because we think man just manufactures a gas that is called argon.
Absolutely. And one of the things just to follow up just finally, I'm just looking for where's can we go there? Air Liquide.
No, it wasn't Air Liquide.
Who was it? Who's our Air Products?
Air Products, yeah.
Air Products, here we go. Air Products, here we go. we're on here. We've been on here numerous times before, but the most important part, search air products.
Argon.
The most important part to. Oh, you got to be joking.
Just products.
Gases. Here we go. Let's see if we can get the page up because it's a bit of a nightmare.
Argon. Top one.
Argon at the top. There we go. We want to get the link with the diagram on it, don't we?
The cryogenic processes.
Cryogenic processes, which are where are they?
Yeah, but that's on the oxygen, isn't it? Making the oxygen.
Making the oxygen. There we go, right there. Cryogenic. Oh, we've got to find it. We've got to find it, otherwise everyone's going to be moaning. No, it's not. We've lost it.
No, we haven't lost it. It's just that we normally go in for
gases, and then we go. I'm sure we go. But anyway, the information's here anyway.
Well, but let's put the image up.
Let's put the image up.
We've got the image up for everybody.
Absolutely.
But as you can tell, all it says is that the argon goes off to be refined or for further processing.
Or they tap off in the distillation column. They tap off an amount specifically for the production of argon.
But they don't tell you exactly what steps they take to make the argon.
Now we have emailed a company to find out a little bit more, because it is our opinion that they actually do process the air that when liquid oxygen or liquid nitrogen even, isn't it?
I don't know.
Because they don't liquefy the air, they liquefy the oxygen and nitrogen. They liquefy that and then they let it evaporate, and then they tap off a small amount for argon production.
Yeah, but from which stream, I couldn't tell you.
From which stream doesn't. Yeah, I couldn't say either. But it's that process that it's our understanding that they further process that stream, whatever gas stream they use. They
and that would involve using caustic potash.
That would involve using a potassium substance of some description.
Yeah.
Now we've emailed. This is only our idea at the moment, you know. Yeah. So it's only possibilities. What we think, given the information we're looking at.
If you go on noble gases.
Noble gases, which is here. Here we go.
See, noble gases. Here we go. Argon is one of them. Noble gases. Historically, also the inert gases, and yet the inert gases, but some of them put out a flame.
Yeah, a lot of them extinguish a flame. So then, how can they be inert?
Yeah.
When you think about it, well, they extinguish the flame, but they can't be inert.
Sometimes referred to as aerogens, make up a group of chemical elements with similar properties. Yeah,
understand.
And the reason why they got similar properties is because they're all mainly made in the same way.
There's only a small difference between them all.
Yeah. They're all odorless, colourless, monatomic gases with very low chemical reactivity. The 6 noble gases that occur naturally are helium, neon, argon, krypton, xenon, and the radioactive radon.
Oganescent.
Is variously predicted to be a noble gas as well.
Absolutely, yeah. But so what we can say,
but they've all got certain distinct colours.
They've all got certain distinct
colours. Neon is neon lighting. You want to look up neon lighting on Wikipedia. Because it makes you wonder what the gas is, or what's lighting being lit up within a neon lighting tube.
Absolutely, yeah. Neon lighting. Here we go. Neon lighting consists of brightly glowing electrified glass tubes or bulbs that contain rarefied neon or other gases. Neon lights are a type of cold cathode gas discharge light. A neon tube is a sealed glass tube with a metal electrode at each end, filled with one of a number of gases at low pressure. High potential of several thousand volts applied to the electrodes ionises the gas in the tube, causing it to emit coloured light.
Now, would you agree that if you're wanting to ionise the gas, you'd need something that contains ions?
You'd need something. You'd need something that would contain
Ions.
ions, because you couldn't have the spark jumping from one end to the other.
Might
could
not
you?
reach, mightn't it?
Might not reach. Absolutely. So you'd want something that would conduct electricity.
Yeah. And what is the best thing to conduct electricity?
Well, I would have thought. Maybe it's quite possible. It's a salt.
Salts, absolutely.
Because
Yeah.
salts conduct electricity. Sodium chloride.
Absolutely.
That's a very big.
Yeah.
Ion. That's a great ion.
Yeah. The colour of the light depends
if you
on
accept ionic theory.
Yeah, the colour of the light depends on the gas in the tube. Neon lights were named for neon, a noble gas which gives off a popular orange light. But other gases and chemicals are used to produce other colours.
But
Now,
other gases and chemicals are used to produce other colours, such
So
as
the giveaways
hydrogen. Absolutely. Helium, carbon dioxide is white.
Now,
Carbon dioxide.
Now, everybody who's watched our videos on CO2 will know that dry ice. What's the colour of dry ice?
Well, it's whitish, isn't it?
White, isn't it?
Absolutely.
When you pressurise the CO2 gas, so it turns to a liquid
from
a gas
to liquid,
and then you revert it back. You can see white within
white, absolutely, yeah.
Within its change of states.
So there's the presence of salt.
There's a presence of a salt.
Our salt acid water pressure system.
Because dry ice, to my understanding, is just concentrated salt, just frozen at low temperatures.
Absolutely, yeah. But it's.
But isn't it interesting how carbon dioxide gives off a white colour when it's used for an electric current to be passed through it?
Absolutely. I mean, it's a very interesting idea, in that basically what gives all of these lights their colours is essentially salts. Derived from different.
And helium would be sodium.
Helium would be sodium. Would be the salt of sodium. Absolutely.
Hydrogen, well, that's probably lithium based.
That could be lithium.
Based.
Or it could be strontium.
Yeah, probably lithium, I'd imagine.
Absolutely, yeah. I don't think it would be calcium based.
But from looking at that apparatus that Cavendish used, which was repeated by Rayleigh, it's easy to know that they actually use an alkali in the base of that jar,
and that alkali is going to affect the resulting gas.
Well, it's going to aid in the production of
that. The
product.
To be fair, I can't see why he's using it. I can't understand why they're using it at all.
Well, if you're a Globie out there and you're watching this video, you've got this far, please tell me, how on earth does that prove that argon is a constituent of the air?
Absolutely, yeah. We'd
Please
love to
tell
know.
me.
Yeah, absolutely.
I'd love to know.
Because these guys, all of this information here, history in this history section, doesn't say anything, doesn't give any indication of how this demonstrates that argon is a constituent of the air.
Yeah.
In fact, to be fair, let's go big time and say there's nothing on this page that demonstrates or proves that argon is a constituent of air.
Yeah.
There's nothing here.
Just what's written.
It's
just a statement.
It's just absolutely. You've got all these references here, all of them, all 47 of them, and yet you won't find any proof that argon is a constituent of air. How ridiculous is that?
Yeah, because in our understanding, it's just a product.
It's just a product like all the others.
They just manipulate, undertaking certain actions like burning this, doing that,
heating this up, passing air over hot metal
to get your product.
Absolutely, of course. There you go. There you have it.
There you go.
Isn't that good?
Eventually, they collide with atoms in the Earth's atmosphere. These collisions usually take place between 80 to 300 kilometers above ground.
The problem is, it's a lie.
Here they cause oxygen and nitrogen to become excited and to emit light in much the same way as in fluorescent lights or in advertising neon signs.
The problem is, it's a lie.
The result is a dazzling dance of green, blue, white and red light in the sky, forming in a ring-shaped area called the Aurora Oval.
What's beyond that